Recording. All right. So today we're going to move on to the A star algorithm. Okay. So it's good to first talk about the why it is needed, and then we'll talk about the actual mechanism. So this is the A star algorithm, and let me see. Do I need to zoom in a little bit? Yeah, I can zoom in just a little bit more. All right. So the A star algorithm is also a path searching algorithm. So it also tries to find the shortest path, just like Dijkstra's algorithm. So the question is, if we already have Dijkstra's algorithm, why do we need the A star algorithm? So the difference is the Dijkstra's algorithm is what we call a breadth first search algorithm, which means it expands the exploration in a quote unquote I'm going to say concentric way. Okay, so imagine this. Imagine that you are at point A and you want to get to point B. The classic Dijkstra's algorithm would expand and explore paths in a concentric way, which means, it will first explore everything around A like this, and then it will further that a little bit, and it will expand that. So by the time you get to B, the circle that it would have explored is gigantic. Okay, so that means you probably would end up exploring a lot of paths that are, let's just say, unnecessary. Okay, so imagine, since we are talking about Utah, so imagine you're in at Salt Lake City and you want to find the shortest route to go to San Francisco. Dijkstra's algorithm would basically say, well, I can tell you how to get to New York, the shortest path, in the attempt to tell you the shortest path to get to San Francisco. You go like, that's a lot of wasted computer cycles. And that's exactly why people also want to have a faster algorithm like A star algorithm. So in the case of A star algorithm, the expansion is not going to be a concentric circle. Hopefully, it is going to be a kind of like this, okay? So it's going to expand a little bit more, but it's going to lean a lot in the right direction. So by the time you find the destination or the shortest path to the destination, you would not have wasted a whole lot of effort on routes that are not even relevant to the shortest path. So the reason why it can do something like this, so remember the red line is A star, and then the blue lines or the blue circles represent the Dijkstra's algorithm. So the reason why A star algorithm can do this has to do with heuristics. Okay, a heuristic is basically a rule of thumb, a quick way to give you a clue. Okay, as to okay, if I need to make a really quick estimate of the actual distance between this point and this point, what would that be? Okay, so that's called a heuristic. All right, so with that context already said, so now we can kind of go into the nitty-gritty of the A star algorithm. So the A star algorithm relies on a heuristic function. So technically, the heuristic function should look like this. Okay, it is mapping the Cartesian product of vertices to vertices, and it's mapping those two tuples to a set of non-negative real numbers. Okay, so it's basically a function. And it usually has to be a quick to compute function, and it has to estimate the actual distance between two vertices. But there's a restriction. It has to be a non-overestimate. So that means the heuristic function can return um, at the most the length of the actual shortest path, but it can be less. So if you want to be lazy and have the easiest possible heuristic function, you can map everything to zero. Okay, so in which case the A star algorithm degenerates into Dijkstra's algorithm. So the behavior would be the same because none of the expansion of the vertices is going to be quote unquote informed because the heuristic is zero for everything. So are we understanding what is the heuristic function? It is a non-overestimate of the length of the shortest path between any two vertices. Are we understanding that statement? Okay. All right. So in reality, if you already know your destination, you can convert the domain into something more like this. So basically, it is just a tuple from any vertex to the destination x, and we are mapping those to non-negative real numbers. So practically speaking, this is what you need, but technically, but you can also have a more general version of the heuristic function. But when you're running an algorithm, you already that when in which case you already know your destination. This is actually just what you need to run the algorithm. All right. So the heuristic function has to be admissible. So what does it mean when the heuristic function is admissible? So the next sentences or the next one sentence, which is really long, is basically what that means. So if we define L as a function as the to represent the actual length of the shortest path between two vertices, then the heuristic function has to return something that is less than or equal to the length of the actual shortest path. So that makes zero possible because no the length of any shortest path cannot be less than zero. So zero is always going to work, except if you use zero, then you're losing the advantage of using a heuristic altogether. So are we still okay, with the second paragraph in the section? Okay, I'm going to assume that we're okay. Um, So the third paragraph said something that I just already said earlier in today's class. If you define the heuristic function to always return zero, that means you're degenerating the A star algorithm into Dijkstra's algorithm. There's no advantage anymore to use the A star algorithm. All right, so now we go into the actual algorithm itself. So we're looking at the graph, okay, which is a two-tuple. We have the set of vertices, we have the set of edges, as usual. We have d as a function that maps the edges to non-negative real numbers, just as before. So in this case, I could not make Dijkstra's, the A star algorithm works the same way as Dijkstra's algorithm. So that means, in this case, you only have one start vertex, which is where you are, and you have one destination vertex. You can only specify one destination in the A star algorithm. So in the algorithm, I'm using s as a as a variable, as a parameter to indicate this is the start vertex, and then x is the destination vertex. So this time we cannot use a set to indicate all the destinations because you only have one single destination. So that's a kind of bigger limitation. And then we have the heuristic function, like we talked about earlier. Even though we usually define it like this, but we don't really need the entire V set as the right-hand side of the Cartesian product. We can just use the set that contains just the destination as the second part. So that would work just fine. All right. So this is where the algorithm actually starts. Okay, for every vertex, do the following to initialize. If the vertex v is not a starting point, then we assign infinities to both the g and the f value of that particular vertex. Otherwise, we initialize g to be 0, and then we initialize f to be the heuristic value between s, which is because the only way to get to the else is v equals to s. So we use the heuristic value of s to the destination, and we use it to initialize the f value. So at this point, it is important to understand what is a G value versus what is an F value. So we're going to go a little bit into that explanation. And this is basically how I write the pseudocode. I give you exactly what operation needs to be performed, but then next to it, without using slash slash, okay? Without using slash slash here, I'm giving you the explanation of what G of something is representing. So if you have a vertex then G of if you have a vertex V, then G of V is the actual length of the shortest known path from the starting point to the vertex V. Okay, so that's how the G value is defined. And this is also why it is initialized to infinity at the beginning, as long as V is not the starting point itself, because we don't know whether there is a path between the starting point and vertex V. Is that okay? Which is analogous to why we define the L value to infinity of anything that is not a destination, except in this case we flip. Instead of using the destination to start with, we're using the start vertex to start with. Okay, so if the G value is the actual length of the shortest path from S to V, then what is the F value? So the F value is a little bit more complex because the F value is the estimated length of the shortest path from S to the destination through V. So that is the tricky part, okay? Because to explain that, so consider A as our starting point and then B as our destination. And now you have some random vertex V somewhere in the graph, okay? The G value is measuring the actual length of the shortest known path from S to V. That is G of V. Very good. We don't really know what is the length of the shortest path from V to X. So instead, we go like, okay, we'll estimate. So this estimation is expressed as H of Vx is the heuristic value from vertex V to vertex X. So when you add these two, okay, when you add G of V and H of Vx, then you have an non-overestimating distance from the start vertex through vertex V to the destination. So let me just kind of pause here to make sure that we all understand what is the F value, because this is the definition of F of V. So instead of having to spell out, oh, this is the summation between the G and the heuristic value, we just call it the F value. So I'll be understanding the meaning of the F value. Okay, all right. So that's exactly why, for the destination itself, the G value is a 0 because the length of the shortest path from the start vertex to the start vertex is a 0 because you're already there. This is also why the F value of the destination is simply the heuristic value from the start vertex to the destination vertex, because we are still using the same equation here, except, the V is actually the start vertex. So are we doing okay so far with the initialization of the G versus the F value? We good? Okay, all right. So now we also have we also have another function called prev or previous. So previous, look at this as a reverse pointer, okay? Because we want to find the actual shortest path, not only the length of the shortest path, but we want to identify the shortest path. So the previous is basically saying, okay, once we get to the destination, how do we figure out what is the path back to the starting point, so that we can actually spell out the actual shortest path? That's the purpose of the previous. So previous V, regardless of whether V itself is the destination or not, is always initialized as undefined. Okay. So later on, we'll start to give it values, but initially it is undefined. So are we still doing okay so far? So here's a quick question. Is undefined actually a value in a programming language? Yes, it is. Nope, it is not. Okay, so in JavaScript, you have null as a value. You also have undefined as a value. They can both can be seen as false, but they're not exactly false. And zero can also be interpreted as false. Undefined is the actual initial value of every variable unless it is initialized in the declaration. Null is returned by some function to indicate it could not find something. So null, undefined are different, but depending on the context, they can both be interpreted as false, and so can zero. And so can the string with zero in it, not spelled out, but the digit zero. Okay, so this is fun stuff, that you can learn in JavaScript. I'm not sure how many of you have already kind of played a little bit with JavaScript, but if you have not, it's actually a really useful programming language because you can do web stuff with JavaScript. You can do server-side stuff with Node.js. You can also do Google Apps Script programming using the same language. Okay, so I find it to be really flexible and really useful. I know most people consider Python to be the Swiss Army knife when it comes to programming languages. I'm sure it is useful, but from my perspective, I think I like JavaScript a little bit better. But anyway, all right. So now we also go through one more initialization. The set O is kind of it does the job of the set Q, but it is initialized to a singleton set with only the starting point vertex or the start vertex in it. So that finishes the whole initialization. And then the rest is this huge mess over here. So what we'll do is instead of explaining the huge mess without a concrete example, we're going to do a trace just like on Monday, if you're here on Monday. Um, and then we'll go ahead and kind of explain how this algorithm works in the context of an example. So we have a pretty messy example here. The solid lines are representing the actual edges and the distances, and then the dotted lines are representing the heuristic value from a vertex to the destination. In this particular graph, the starting point is node number, I cannot remember which one is the beginning. We can use node 1 or node 5 as the beginning. And then the destination is node 6. Okay, so X is definitely the destination, but we can choose node 5 or node 1 as the beginning. So are we doing okay so far in terms of how to read the graphical representation, differentiating between the solid line versus the dotted lines? Okay, all right, so looks like we got that. Okay, so what I'll do is I'll do the same thing that I did the other day. I'm going to shrink the picture a little bit, just so that it doesn't take up a lot of space when I display that. Okay, so we'll go ahead and take a snapshot. This might still be too big, but we'll see. Ah, nope. One more time. Okay, that looks good. All right, so I'm going to put it all the way up here. Just like we have a template for following Dijkstra's algorithm, I also made another one to follow the A star algorithm. So this is just a template. So we can make a duplicate of the template. So we can say make a copy. And then we'll change the name of that new spreadsheet or Google Sheets into today's date. Okay, so we're going to open this up. All right, and then give it a name based on today's date, 2025, November 26th. There we go. All right, so I'm going to move this one a little bit, maybe over here. All right, so this one is a little bit too big. We don't need all the columns. So I'm going to go ahead and delete some of the columns that I don't really need. Okay, because we only have 6 vertices in our example. So all of these are not needed. So I can either hide them or you can delete. We can just delete in this case. And then the vertices are not letters, they are digits. So we have 1, 2, 3, 4, 5, 6 instead of A, B, C, D, E, F. The reason why I switch everything to digits instead of letters is because I also have f as a function name and d as a distance and so on. So using digits to represent the vertices is a little bit cleaner, so there's no quote unquote collision of names. All right. Do we have any questions about how to set up this thing for now? No. Okay. All right. So I can make it a little bit narrower just so that I have a little bit more space later on to also show the graph as much as possible. So I can stash this here. Ah, perfect. Okay, I just freed up just enough room to do this. All right, so we're going to do some initialization. Remember, every vertex that is not a destination is going to have a g and f value of infinity. We know vertex 6 has to be the destination. Do you have any preference as to which one you want to use as the start vertex? Between 5 and 1. 5? Okay, we can do 5. So 5 is the starting point, 6 is the destination. So that means, the g value of the destination, number 6, is going to be 0. Okay, I use shouldn't be doing that. Should be doing this over here. And then it will automatically update row 3, just like the same way as the Dijkstra's algorithm template would do. All right, so the f value of 6 is going to be the heuristic value from, let me see. Nope, I got it backwards. Sorry, I got it backwards. So because we have to start with a start vertex, and which one did we choose? 5, right? So 5 is the start vertex. So this one, the g value of 5 is going to be 0 because 5 is the starting point. The length of the shortest path from the starting point to the starting point is guaranteed a 0. On the other hand, if I want to estimate, okay, what is the length of the shortest path from vertex 5 to the destination, which is vertex 6, the heuristic value says is 13. Okay, so that's why we put a 13 here. And then everything else are infinity. So I'm just going to spell INF, to represent infinity because I forgot how to put in uh, the code for the infinity symbol. All right, so for the previous, everything is undefined. So I'm going to use UND for undefined, UND, 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 and then one more time, UND. The set O is initialized to a set that only has the starting point, which we agreed to be vertex 5. So that's the initial condition. This is how we initialize everything before we get into the while loop. Are we doing okay so far in terms of the initialization of all the variables? Okay, we're good. All right. So now we get into the algorithm. So the algorithm, the A star algorithm, has a more complicated condition for the loop. So we'll go take a look at the condition of the loop here. So this is the condition of the loop. As long as this condition is true, we stay in the loop. When this condition is false, then we exit the loop. So what is it saying? This is, okay, what is this? We should note what this symbol is representing now. Their existential quantifier. So it says there exists a vertex V in the set O such that f of V is less than g of x. Okay, so what do we do? How do we evaluate this given the state of everything that we have now? Well, we only have one vertex. Hmm? 13 is bigger than 5, and therefore it is true. Well, what is g of x? No. Okay, so let's go back. Okay, go back a little bit more. The g value is the length of the shortest path from the from that vertex to the destination. Huh? F of x is f of v is the sum of g of v and h of vx. You don't have to remember anything because it is ta-da, up here, right? So g of x is the length of the shortest path from the start vertex to the destination. Okay, I haven't explored a single thing. How can I possibly know the length of the actual shortest path of from the start vertex to the destination? I cannot. So how was it initialized? Infinity. Okay, it was initialized to infinity. So g of x is initialized to infinity. What about f of s? Because since the set O only has an element of s right now, so the only element we need to consider is f of s. So how was f of s defined? It's the start vertex, right? How was the f value of the start vertex defined? In other words, you plug in you plug in S as V, V as S, and so on. So it becomes really just the H value or the heuristic value from the start vertex to the destination. So that would be 13. So the question now is, can I find a vertex in O so that the f of v value, which is f of s in this case, is less than g of x, which is g of 6, because 6 is our destination. Is 13 less than infinity? Okay, so I think we agree that this quantified expression is true. Okay, very good. So that means we got stuff to do. Okay, so the stuff that we need to do is the first line is saying, okay, we are going to pick an element out of O such that, okay, so we'll go ahead and do this. So we are going to pick an element out of O such that for all elements W in O, f of c has to be less than or equal to f of w. What is that saying? And I have the answer already, so I'm going to cover it up before you guys start to read it. So what does that mean? We have seen stuff like this already. Okay, it is trying to find the vertex in O. So we are trying to find the one that has the least f value. So by this time, I really hope that you can read this kind of notation, because this is this is the class to build up your vocabulary to read mathematical notation, because you need that in the upper division classes that you're going to go to. So that expression, the whole thing about this particular expression here is to say, oh, we want a vertex C where the f value of vertex C is the least among all the vertices in O as a set. Are we doing okay so far with that? All right. So now we look at our actual trace, okay, to find out, okay, what can that possibly be? We only have one element in the set O. I think we can just say that it is the one that we're going to choose. So that's why we choose that, okay, as variable C. And then after that, we delete it from, or we remove it from the set O, just like here we did with set Q once we pick V as a vertex. So now we have to look at all the neighbors, but this time N is an outgoing neighbor. In other words, we are looking at all the things that are reachable using a single edge from vertex 5. So how many do we have? Okay, so how many edges are coming out of vertex 5? There's only one, not counting the dotted line, right? Because only the solid line are edges. So there's only one single edge coming out of 5. It is going to vertex 1. So that means the only outgoing neighbor that I need to be concerned about is vertex 1. So now we're going to figure out the value of t. So the value of t, if we go back to the algorithm here, so the value of t is calculated this way. It is g of c plus the distance of C to N. Okay, so we look at this one here, and then we switch back to, oh, not this. We switch back here. So the question now is, if I want to um, if I want to calculate the length of a path, not necessarily the shortest, if I want to calculate the length of a path to vertex 1 through vertex 5, what would that be? What is the length of the shortest path from the start vertex going through vertex 5 to vertex 1? That is the question. What do you think? Okay, first of all, what is the length of the shortest path from the starting from the start vertex to vertex 5? It's 0 because vertex 5 is our chosen starting point. Okay, so what happens when you add the distance of the edge from vertex 5 to vertex 1? 0 plus 5 is a 5. Okay, so t, local variable t, has a value of 5. Oops, nice picture. It's actually a picture from my office, but then I lose the other one because it's using the same instance. Okay, so we have to bring it back. Uh, do it one more time. Okay. Mm, all right, now it's back. Alrighty. So t is 5. Okay, that's what we calculated last time. The algorithm then wants to compare. So when you look at the algorithm, which I will return back to the normal size plus a little bit more. So the algorithm wants to compare, we are down to here. So the algorithm wants to compare t, which is here, versus g of n. Okay, so remember that. Okay, it is helpful if you already have your own printout or your computer showing the algorithm. So so when I jump between the two, you don't have to lose the context. All right, so we go back here. What is g of n at this point? N is 1, so I'm asking what is g of 1? It's infinity. Very good. So the question is 5, which is representing a path, a newly found path from the start vertex to vertex 1, and it has a length of 5. Is it beating the length of the current quote unquote shortest path from the start vertex to vertex 1? Okay, very good. So we got a bunch of stuff to update because we have to first update g of 1 and say, oh, you're supposed to be a 5. And then we also have to update f because now we know that in order to go from the start vertex to vertex 1, the shortest path is 1. But if I were to go through vertex 1 to the destination, I'm going to have to add this 5 here. So that means the f of 1 is going to be a 10. And in order to go to vertex 1, the previous vertex is going to be vertex 5. So this way I have a back pointer pointing backward so that I know how did I get to vertex 1. Well, we got to vertex 1 through vertex 5, which kind of makes sense because it's the start vertex at this point. Okay? And because we did all these updates, we also have to add vertex 1 now to the set O. Are we good? All right. So that completes the for each loop because there's only one outgoing neighbor from the perspective of vertex 5. So now we go back to the while loop. All right, so let me show you the while loop because it's important to reevaluate this condition. So the while loop is going to ask this question again. Is there at least one vertex in the set O such that the f value of that particular vertex is less than the g value of the destination? So what do you think? So did we update the g value of the destination? which is g of x6 for us? We did not. So that means it has to be still infinity. Okay. So when we look at that, it is still an infinity right here. Okay. So now we are asking, um, if we look at all the vertices, there's only one in O. What is the f value of 1? We just updated it. 10. Okay. Because we see it is here. Okay. It is 10. Is 10 less than infinity? Okay. Well, in that case, we got stuff to do. So now we go here. We're going to pick um, the vertex in the set O that has the smallest f value. When you only have one item in the set, you don't really have to do much comparison, don't you? You don't have a choice. So we're gonna have to say, yeah, we don't have a choice. We're gonna pick vertex one over here, which means now we move vertex one from the set O, and now we have to list or enumerate all the outgoing edges from vertex one and identify all the neighbors. Okay, so how many outgoing solid lines do we have coming out of vertex 1? There are 3 of them. So they go to vertices 2, 3, and 4 respectively. How do you guys want to order this? Because once again, we have 6 choices. 3, 4, 2. Okay, so we can do 3, 4, and 2. Okay, very good. So we'll deal with it one at a time, right? So if we look at vertex 3, what is the corresponding value of t? In other words, I might have just found a new path from the start vertex through vertex 1 to vertex 3. What is the length of that path? Hmm? It is not 5 because it takes me 5 to go from the start vertex to vertex 1 already. But in order to go from vertex 1 to vertex 3, we have to add another 5 to it, so it's 10. Okay, so 10 is the value of this t, because the t or the variable t is really indicating if I were to go from the start vertex through vertex c in order to get to vertex n through the edge of cn, what would that cost me? Okay, in other words, I'm calculating the length of a path, not necessarily the one shorter than the one before, but it is a path. So now I have to compare this 10, which is representing the length of a path from the start vertex through vertex 1 to vertex 3, and I'm comparing this to the current length of the shortest path from the start vertex to vertex 3. What is that? Okay, let me ask you one question at a time. Is it f of 3 or is it g of 3? It's g of 3. That is correct. And g of 3 is infinity right now. It's 10 less than infinity. Yep. So in other words, we just quote unquote found a shorter path from the start vertex to vertex 3. That is the significance of meeting that condition. It says we have just found a shorter path. So once we found a shorter path, we got a bunch of stuff to update. So this will become 10, okay, because your g of 3 is trying to remember what is the length of the shortest known path from the start vertex to vertex 3. F of 3 also needs to update because of how f is defined. So that means we just have to add um, the heuristic value from 3 to 6, and that's just 1. So now it is 11 over here. In order to get to vertex 3 through what we have discovered up to this point, you should go to vertex 3 through vertex 1. So we put a 1 over here. And because vertex 3 is updated, if we just found a shorter path to vertex 3, we have to add vertex 3 to the set O. Are we still doing okay so far with this? Okay. So now we go for the next iteration of the for each loop. Now we look at vertex 4. So once again, okay, what is the length of the path from the start vertex through vertex 1 to vertex 4? So that would be, to get to vertex 1, it will cost me 5 already, okay, because g of 1 is 5. The edge from 1 to 4 has a distance of 2. So 5 plus 2 is 7. So that's why t is now a 7. And I have to compare this 7, which is the length of a path from the start vertex to vertex 4. And I'm going to have to compare that to the length of the shortest known path from the start vertex to vertex 4. And what would that be? What is the length of the shortest known path from the start vertex to vertex 4? Infinity, that is correct. And that's because we are looking at column H. 7 is less than infinity. So once again, we got a bunch of stuff to update. This is going to be 7. This is going to be 7 plus the heuristic value from vertex 4 to the destination, which is 0. Okay? So once again, that is actually okay. Okay? If you cannot figure it out, yeah, put in a 0. So in order to get to vertex 4, we should go through vertex 1. So that means the previous vertex of vertex 4 is also just vertex 1. So now we work with the last one, which is vertex 2, to get to go from the start vertex through vertex 1 to vertex 2. We're having this 5 here, but we're also having to add this 8 over here. 5 plus 8 is a 13. Well, it sounds horrible, but it's still okay. It still beats the length of the current shortest path because we actually do not have a path at all at this point. So that means this also updates to 13. And then this one over here is updated to 13 plus, what was it? 13 plus, we're looking at 13 plus 2. So that would make it 15, like so. So are we doing okay so far? Okay. Oh, I forgot two things because every time I update the G value of something, I have to add it to the set. So 4 has to be added here, and then 2 has to be added here. All right. So we are now done with the for each loop. We go back to the beginning, which is the while loop. So when we go back to the while loop, we're asking that very same question, which is there at least one vertex in O such that the f value of that vertex is less than the g value of the destination? We know the destination is vertex 6, so we're actually just trying to say it's g of 6. So what do you think? So we look at the vertices 3, 4, and 2, and we ask, is at least the one does at least one of these vertices have an f value that is less than g of 6? What is g of 6 at this point? It's still infinity. We haven't touched that. So if you look at f of v, f of 3, sorry, f of 3 is 11. That's less than infinity already. I think we can stop, okay? Because we have confirmed that at least one element in the set of O has a f value that is less than the g value of the destination. All right, but what does that mean exactly? Okay, in other words, if I switch back to the algorithm, what does that mean exactly? So you have to remember what the f value is representing. It is representing the length of a path from the start vertex through vertex v to the destination. In other words, it is an estimated length, okay, of a path between the start and the destination. If that estimation is less than the g of x, which is the length of the shortest known path at this point, that means we have hope to find a shorter path. Does that make sense? I want you to kind of think about this a little bit because understanding why that expression is important will help you understand also by the time you trace the algorithm why you have to do what you need to do. Are we doing okay so far with the rationale of this expression? Okay? Because the opposite way to look at this is to say every vertex in O, every single one, has an f value that is greater than or equal to g of x. So what that means is for every vertex inside O, the shortest path, even though we may not have explored the entire thing, but we are guaranteeing that all of those paths will have a length that is greater than the length of the shortest known path to the destination already. So that means there's no need to explore any further. Now, if you explore any further, you won't hurt the algorithm. You won't accidentally identify a path that is not the shortest path, but it would be a waste of cycles. Okay, so I just want to make sure that that part is clear. If you're not really sure what I'm talking about, mark the time so you can re-watch this portion over, and try to think, what I was trying to say or what I meant when I said what I said. All right, so we move into here, and then the next thing we need to do is to identify one single vertex in set O where it has the smallest f value compared to other vertices. So when you go to the trace, we have three to consider this time. Okay, so now you have to look at f of 3, f of 4, and also f of 2, and ask which one has the smallest value, which one has the smallest f value. The best way to do it is to look at row 3 because row 3 keeps track of all the updates. So we are comparing f of 2, f of 4, and also f of 3. And I think the winner is pretty clear. So which one would you choose? 4. Okay, very good. So we're going to pick 4 as our winner. And then we have to take it out of the set here. Now we have to look at all the outgoing edges of vertex 4. It has two. One is going to 3 directly, one is going to 6. So which one do you want? How do you want me to order that? 3 and then 6, or 6 and then 3? 3, 6. Okay. So we'll go for 3 and 6. So now this is fun because now we are going like, oh, we got to 3 already. We know how to get to 3. Look at this. We got to 3 through 1, and then we get to 1 through 5, and 5 is the start vertex. We have found a path to vertex 3 already. Do we have to reconsider? The answer is yes, you have to reconsider. Okay? So once again, we're trying to calculate the value of t, which is the g value of 4 plus the distance of the edge for 3. Okay? So what would that be? Well, we can just look it up. Look at the g value of vertex 4. It is currently a 7. So you add the edge or the distance of the edge for 3, which is 2 to 7. It is 9. What is this 9 representing? This 9 is representing the length of a path from the start vertex through vertex 4 to vertex 3. Okay? That path has a length of 9. The question is, did I just find a shorter path to vertex 3? Well, let's find out. What is the length of the shortest known path to vertex 3, which is g of 3? What is g of 3 right now? It is 10. Is 9 less than 10? Okay, well, that tells me that we just found a shorter path. Okay, so now we have a bunch of stuff to update again. This is now 9, and then this is now 1 less than that, which is 10. And then we also have to update how are we supposed to get to vertex 3? Oh, we don't want to go through vertex 1 anymore, um, because we want to go through vertex 4 this time. And then we also want to make sure that 3 is added to the set, but since it's already in the set, it is not a big deal. Are we doing okay so far? All right. So now we move on to vertex 6, which is our destination. We go like, woohoo! Oh, we are almost done. No, no, look at the clock. We still got half an hour, so we're not even close to being done. Ah, all right. So we do the same calculation. Just because um, n as a variable is already the destination doesn't mean that you have to do any special consideration. Okay, you do the calculations exactly the same way as before. So now we are asking, okay, in order to go from the start vertex through vertex 4 to vertex 6, what is the length of that path? We know that in order to get to vertex 4, it will cost us 7. Okay, that's the length of the shortest path to from the start vertex to vertex 4. The arc or the edge from 4 to 6 is over here. Ooh, that is super expensive. It is 20. Okay, so now we are adding that 20 to the 7. That makes it 27. Okay, if I rem if my math is right. Okay, so I can always use equations here too because we are referring to this 7 here. So if I want to use equation, I would say this is this 7 over here, which is g of 4, and then plus the edge, which I don't have anything on the spreadsheet with. So that would be adding the 20 over here. Oops, 20. That's 27. Pretty expensive. But if you compare the 27, which is the length of a path, right, from the start vertex through vertex 4 to vertex 6, which is our destination, it will cost us 27 units. Is it less than the length of the shortest path, the shortest known path to the destination? Yep, because the shortest known path to the destination is infinity. This is the first time that we find a path from the start vertex to the destination. So we go like, oh, cool. We just found a path to the destination. Let's do a bunch of updates. Okay, this 27, 27, and this is going to be 4. And we can now add the destination to the set. Oh, okay, like so. Are we good so far? Okay, all right. So now we go back to the while loop. Oh, wrong thing. We go back to the while loop and then we ask this question again. Of all the vertices in the set O, does at least one of them have an f value that is less than the g value of the destination, which is g of 6? Okay, so this time it is not as obvious, okay, because before g of 6 had been infinity. Okay, everything, anything, any actual integer is going to be less than infinity. Not so much this time, okay, because this time we are now looking at 3, 6, and 2. So we are looking at f of 2, f of 3, and then f of, why is this not updating? Ugh. Okay, refresh. Now it's updating fine, but it did not take my last update. Okay, fine. We'll have to do the updates again. Something didn't work last time. So this is 27, and this is going to be 4, and then we have to add 4 to the set, like so. All right. Huh? Oh, add 6. You're correct. Add 6 to the set. There we go. Thank you. So now we have to look at 3, 2, and 6. Look at those particular f values. So we are looking at f of 3, f of 2, and also f of 6. And then we ask, is at least one of these three less than g of x, which is 27? Yeah, we got two that are less than g of 6. So we go like, okay, we have another iteration. So now we have to choose a vertex out of O where the f value is the smallest among the all the ones. So we are looking at f of 3, f of 2, sorry, f of 2, f of 3, and f of 6. Which one is the smallest? 3, right? Okay, so we choose 3 out of the whole set, get it out of the set O, and now we have to look at all the outgoing edges of vertex 3. So vertex 3 is right here. It has two outgoing edges. One is 2 and one is 6. This time I'm going to choose 6 first. You guys get to choose sometimes, and I get to choose some other times. All right. So if I get to 6 first, okay, it's like, oh, we just found another path to 6 to the destination, but this time we're going through vertex 3. to go to vertex 6. The last time we were going through vertex 4 to vertex 6. So what is the length of the path from the start vertex to vertex 3, and then from vertex 3 to vertex 6 through an edge? So to get to vertex 3, the length of the current shortest known path is a 9. And then to go from vertex 3 to vertex 6, that edge has a distance of 10. So that means we are adding 9 to 10, which is 19. Okay, so our t is 19. So this 19 is representing the length of a path from the start vertex through vertex 3 to vertex 6. The question is, did I just find a shorter path? The answer is yes, I just find a shorter path because if I compare this 19 to g of 6 at this point, which is 27, yeah, we got a shorter path. Okay, so that means we have to update again. So now we update the vertex 6. So whether vertex 6 is really the destination or not doesn't even factor into the calculation. The algorithm does not care at this point. So we just go like, oh, okay, 19 is the length of the shortest known path. We just found one that is shorter. So we update this, we update this, and then we also have to update this and say, hey, if you want to get to the destination using the shortest path, do not go through vertex 4 first, okay? Go through vertex 3 first. There we go. So now we also have to add vertex 6, into the set, but it's already in the set, so it doesn't look like we have made any changes. Are we doing okay so far with this? Okay. So now we go to vertex 2, okay, and we ask, all right, vertex 2 is right here. It has one single outgoing edge to the destination. So now we ask, hey, if we are to go, no, I take it back. We're supposed to go from vertex 3 to vertex 2. So now we are asking, hey, if we are to go from the start vertex through vertex 3 to vertex 2, what is the length of that path? G of 3 is a 9, and then we add the 9 to the 2, so that would be 11. All right. So the question is, did I just find a shorter? Did I just find a shorter path to vertex 2? G of 2 is 13 at this point. Now we have 11. Yep, we just found a shorter path from the start vertex through vertex 3 to vertex 2. But the answer is yes, there is a shorter path. This is the length of the shorter path. And then we also have to update the f value to vertex 2. And we have to add 2 to the g value. So this would be 13 now. And then we also have to update, hey, if you want to get to vertex 2, oh, last time I went to vertex 2, I forgot to update. That was my bad. Okay, there we go. So this time we're going through vertex 3 to vertex 2. So now there's a 3 over here. And we have to add vertex 2 to the set O simply because we just changed its G value. But it's already in the set, which is okay. It's not a problem. All right, so we have now concluded the for each loop. We go back to the while loop. And the while loop is asking the same question. Out of these two vertices, does at least one of them have a f value that is less than g of 6? So let's highlight those values. This is f of 2, and this is f of 6. Is at least one of them less than g of x, which is 19? Yeah, I think we have this one being less than. So we are good. We cleared the condition. Yes, because they're the destination. Yep, because the heuristic value from 6 to 6 has to be 0. Yep. All right, so we know that we can continue with the while loop and choose, in this case, vertex 2 as C. So we now only have 6 left in the set O. And now we look at vertex 2 and ask, okay, what are your outgoing edges? There's only one going to vertex 6. So this time neither I nor you guys get to choose because there's only one. Okay, so now we ask, what is the length of the path from the start vertex through vertex 2 to vertex 6? To get to vertex 2, the length of that path is 11, and then you add the edge from vertex 2 to vertex 6, which is also 2. Um, well, not also 2, but 2. So that is 9 plus 2, or 11 plus 2 is a 13. So that would be a 13 here. Are we still good? Are we still understanding why we have a 13 here? Okay. So that 13 is here, and we are asking, did we just find a shorter path to vertex 6? G of 6 is 19, and the length of the new path that we discovered has a length of 13. So yes, we found a shorter path again to the destination. So we have a bunch of stuff to update again. Okay, this is now 13. This is also now 13. This is now 2 because the shortest path to the destination is to go through vertex 2, not vertex 3 anymore. And then we also have to add the destination vertex back to the set O, but it's already here. No big deal. So now we are exiting the for each loop. We go all the way back to the beginning. And once again, we have to ask the question, out of all the vertices of set O, do we have at least one vertex in set O that has a f value that is less than the g value of 6? What do you think? Nope. The answer is no, which means the condition of the while loop is false, which also means we're done. So we are done with one element left in set O. So now the question is, what is the shortest path then? We don't have an E prime here to keep track of all the edges to find the shortest path. So the way you figure out the shortest path is to start with the destination, number 6, and the previous is 2. Then you go to 2 and you say, oh, okay, to get to 2, we have to go through 3. And then to go to 3, you have to go through 4. And then to go through 4, you have to go through 1. And then to go through 1, you have to start with 5. Okay, so that's how we backtrack the shortest path. So in this case, I specifically made the heuristic to trick the A star algorithm so that the first time we touch the destination is not the shortest path. The second time, also not the shortest path. We updated, the length to the shortest path 3 times before we get to the optimal one. So the number of hops have nothing to do with the actual distance, because in this case, to get to number 6, we have to go through number 2, and then to get to number 2, we have to go to number 3. To get to number 3, we have to go to 4, and then to get to 4, we have to get to 1. And this time we don't have a choice because there's only one edge over here. So the the path that is the shortest also has the longest. It also has the most number of hops, or I should say, number of edges along that path. All right, so that's a trace using the A star algorithm. Do we have any questions about how this works? No questions? Okay. All right. So we have covered Dijkstra's algorithm and now the A star algorithm. The A star algorithm is a little bit more complex because we have to keep track of F and G. The F value is not necessary because it is by definition the G value plus the heuristic value. So we could have just computed that dynamically on the fly every single time. It's just a little bit harder to do that when you also have to choose amongst the vertices in O, which one has the smallest F value. So if we do not keep the F value by themselves and recompute the values every single time, it's just going to be a little bit more chore, but it's possible. All right. Any questions? No questions? You guys are thinking about pumpkin pie and turkeys, aren't you? Okay. I should have named the vertices like, you know, Mayflower and then turkey pumpkin pie, and so on. What is the shortest path to your Thanksgiving holiday? Definitely not through CISP 440, right? All right. Well, I'm gonna cut today's class a little bit short, just so that you guys can leave a little bit early and go enjoy your holiday. I will see you on Monday. Have a nice weekend. But don't forget you have a homework assignment, okay, for Dijkstra's algorithm. And then right after that, we'll have another homework assignment for A star algorithm, which is kind of the same as what I just did, okay? So understanding the algorithm is super important, not just mechanically, but why it works. Okay, so focus on why it works. What does it mean for this statement to execute? What does it mean for this condition to be true, and so on? Those are the questions that will take some time for you to kind of let it sink in. All right, I am going to stop the recorder. Yes, I got it recorded. Don't worry. And I'll see you guys on Monday. Have a nice weekend.